Professor Onur Mutlu. He's a professor in Information Technology and Electrical Engineering Department at ETH Zurich, and he's also an adjunct professor at Carnegie Mellon University. So today his talk is about storage-centric computing for modern data-intensive workload. Please welcome our speaker.
Okay, thank you very much. Thank you very much for the introduction, and thank you for inviting me to this event. I'm happy to talk about storage-centric computing today with a focus on some modern data-intensive workloads, especially genomics. I have a lot of slides. I'll motivate this first, and then we'll see how much we can cover. Today, computing is bottlenecked by data. If this was, as was mentioned before in both of the prior introductions, all important workloads are data-intensive. They require rapid and efficient processing on large amounts of data. And on top of this, data is increasing. We can generate more data than we can process, and we need to perform sophisticated analyses on more data. And this is an example that was earlier mentioned. Basically, if you look at neural networks, machine learning, these are some modern workloads. Compute requirements is increasing, data requirements are increasing. They're both increasing exponentially, and we need to put computing and storage together so that we can actually achieve much better systems going into the future. It's not just in machine learning. There are a lot of applications like graph analytics, databases, data center workloads, where data is a performance energy bottleneck. On the mobile end, we have similar problems, basically. There are mobile applications that are increasingly working on data, and data is a performance energy bottleneck on those as well. I'll talk a little bit about genomics. I'll go back to that later in the talk as well. This is an area where we can generate a whole lot more data than we can process. Oh, I don't see the thing over here, but if you look over there at the inflection point, what this shows is the cost of genome sequencing, and cost of sequenced genome is reducing exponentially, much faster with the introduction of new technologies that can sequence the genome. And if you look at that linear curve, that looks linear over there, but it's really a log scale on the y-axis, you see that that's Moore's law. Basically, the cost of a transistor is reducing much slower than the cost of sequencing genomes. This means that the data generation capability is much faster than the computing capability. And you can see that happening in many domains. And clearly, we have a problem at hand if this is the case, because scientific discoveries and medical advancements, a lot of things that rely on genomics is bottlenecked by how fast we can process the data and how efficiently. And clearly, there are many examples of genomics. I don't want to go into this today in detail. COVID-19 has taught us one very, very specific and small example. There's a lot more to see. And this is one data generator. Do we have something that shows? I don't see it over here. Oh, you don't have it. Okay, I'll come over here then. Basically, it's a data generator, as you can see. It's a device that can generate data very well. Unfortunately, you cannot process data very well with this thing because you don't have any computation capability. So you have to move the data far away. Once you move the data far away, you go to a data center, for example, where you have a lot of storage. But then within the data center, you need to move the data a lot to actually process the data that a lot of these devices generate. So data is a huge performance energy bottleneck. So let me summarize the problem. Basically, the problem is we have a lot of good devices that can generate data. This is one genomics machine. They're a very special purpose. And then we move the data far away from them to process the data on general purpose computers that can do analysis. And this picture is very similar in many modern data-intensive applications. This could be genomics. This could be some data that's used for machine learning later. This could be a lot of video, for example, that's generated. It's all over the place. And that's the problem we're having, in my opinion. So I can talk more about genomics a lot. We're doing a lot of algorithm architecture co-design, both from a processor-centric perspective as well as a data-centric perspective. Everything we're doing is interesting, I think, and that can be applied to storage. And I believe actually storage is the right place to apply a lot of these ideas. I will not bore you with a lot of these, but I'll give you one example. So what can you do today? Today, you can actually accelerate things using FPGAs, which is interesting, but it's not the future, in my opinion. The future is bigger. Basically, you can take a CPU and you can offload some computation to a quite powerful FPGA that has high bandwidth memory access. And we did this for many applications. One example was weather modeling. Another example was genome analysis. And you get significant performance and energy improvements. And these are not small numbers, as you can see. Of course, you need to customize the thing that you're offloading to the FPGA, and you need to actually take advantage of the memory bandwidth. But these are good numbers by moving things to be more data-centric. This is a near memory computation engine. I believe near storage is going to be even more interesting because you can have near memory inside the storage and near storage inside the storage as well. Okay, so let me go over these relatively quickly. I'm going to talk about in-storage genome filtering later on, but there are a lot of interesting algorithms that are very much bottlenecked by data today, and it's really bottlenecked by the storage capability and communication capability. Okay, if you're interested, there's a lot more in genome analysis. I think the point is that data is really overwhelming modern machines today. It's overwhelming our storage and memory capability, communication capability, and computation capability in the end. Mainly because of the way we're designing our systems, in my opinion. It greatly impacts robustness, as was mentioned earlier, energy, performance, and cost as well. I'm not going to talk about robustness in this talk, but it's extremely important, reliability, safety, and security of our systems. Now, if you go back to the fundamentals, if you want to design a computing system, you need computation, communication, storage, and memory. And we've heavily optimized this computing system, and we've kind of ignored the rest. We've basically centered everything around this computing unit, which I believe is the wrong thing to do. Maybe we should be centering things around something else and more equally balancing these components. If you look at a computing unit, it looks like this today. Basically, computation is done on a very small fraction of the machine. Everything is dedicated for data storage and movement. Caches, interconnects, other caches, other interconnects, other caches, other interconnects, other caches, memory, other interconnects, storage. Basically, most of the system is dedicated to storing and moving data, yet the system is still bottlenecked by memory and storage. You would expect that the system would not be bottlenecked by memory and storage because we were dedicating almost all of our resources to it. Okay, you don't like my picture? This is AMD's picture. Basically, most of the system is caches. And then they're adding more caches, 3D stacked. You don't like AMD? There's IBM's picture. Most of the system is caches, and they're adding more caches. And I could give you more pictures here. This is a computing unit with a lot of caches, essentially a lot of SRAM, and then a lot of DRAM, and the darkness where storage is. And maybe we should really be designing the system such that we can process data everywhere as opposed to moving everything over here. Okay, and let me give you some numbers. So we've analyzed a lot of these workloads. I'll give you two data points, basically. On these workloads that we analyzed together with Google, we found out that more than 60% of the total system energy is spent on data movement. And that's small, I think. If you look at actually large machine learning models executed on, let's say, state-of-the-art accelerators, you see that more than 90% of the total system energy is spent on memory. And we're not even including storage here. Once you include storage, things become even worse. People are trying to avoid storage because storage is not able to do computation, and as a result, you have to move the data to a computing unit. But if storage was able to do computation, then you could actually do a whole lot more, and you won't see this bottleneck, in my opinion. Or the bottleneck will shift, and you'll need to optimize something else. So let me give you our vision on an intelligent architecture, and I'll give you some examples from Genomics relatively quickly. I believe that intelligent architectures need to handle data well. Today, we're not handling data well. So what does handling data well mean? We should ensure that data doesn't overwhelm the components that we're designing. Today, they're overwhelming our components. We should take advantage of vast amounts of data and metadata that's flowing through the system. We should make more data-driven decisions in our systems as opposed to human-driven decisions. This was actually mentioned in one of the earlier talks. I don't have time to go over this, but we're making a lot of human-driven decisions in our systems that's actually making our systems quite suboptimal. And then there's a lot of, this was also mentioned in earlier talks, there's a lot of properties of data that we're not exposing and exploiting in our systems. Data has lots of properties: privacy, security, approximability, error tolerance, locality, even performance. None of these properties are really exposed at a general purpose level in our systems and put down into the storage, memory system, and also the computing system. As a result, our systems are making decisions blindly based on structures as opposed to the properties of data. So, for example, if I design a memory controller or storage controller, it doesn't know if this piece of data is more important than this piece of data from a security perspective or privacy perspective. We need to provide that information to our systems. So this is the vision. Let's say we need to make our computing systems much more data-centric than processor-centric. I'm going to talk about that. We need to make our systems to enable data-driven decisions as opposed to designer-dictated human-driven decisions. And we need to expose data characteristics to our systems such that we make data characteristic-aware decisions as opposed to component-based decisions. There's a lot to do in all of these. And this is really an across-the-stack problem. But I believe we can actually start step by step, as I will show you with a couple of examples quickly. OK, if you're interested in more, I'm happy to talk about this. Let's jump into the first part of this. Even if you look at the first part, data-centric or memory-centric systems, there's a lot to do over here. First, I'm going to talk about the first one, doing processing close to where data resides. But we also need to design our systems to be much more lower latency and lower energy. And we're having a lot of trouble with this, I think. We need to have low-cost data storage and processing at high reliability and intelligent data management, again, for high reliability, robustness, security, etc. Let's jump into the first one. I call this processing data where it makes sense. Today, we have no option. we process the data in the computing unit. But data actually is generated in the sensors, and they actually are stored in everything else almost, but the computing unit. So why don't we actually have processing capability in all of those places and have a coordinated system of distributed agents? So this is not a new idea. People have proposed processing in memory. This is from 1960s. If you find a new paper, please let me know. These are beautiful papers that propose the original ideas. I'm not going to go over them. Why is it interesting today? I believe today we have nowhere to escape. We're having problems with memory technologies, many of them at the same time, main memory. We're having a lot of problems with applications and systems. I'm going to talk more about this part today. Data access is a bottleneck, energy and power are huge bottlenecks, and data movement energy dominates computation energy today. And we need performance, energy, and sustainability at the same time. We don't want a trade-off between these three. And I believe we can improve all metrics by minimizing data movement and rethinking our systems. Okay, so this is one example over here that shows the disparity between the energy to do a complex arithmetic operation and the energy to do a memory access. That's 800x difference. If you go to storage, that amplifies by another order of magnitude, depending on the technology that you have in storage. I don't want to call storage specifically based on one technology, because there are many technologies present in the storage device, which makes it really interesting for computation. So this is the problem, basically. We do not want to move data. We want to enable computation with minimal data movement, compute where it makes sense, where data resides, and where it's generated, and make computing architectures much more data-centric. Clearly, there's a lot to do here. If you look at even just memory and storage, we need to be able to tell these devices, basically send them queries. Can you do this operation for me? And please do it for me if you can. And the results get generated. Even this is an accelerator model. I think this is short term, but longer term than where we are today. In the longer term, these are all equal agents. We're not going to have accelerators, in my opinion. Let's see if we get there. There are many questions over here, which I'm not going to go into right now, but software and hardware interfaces need to change. System software compilers and languages need to be changing. And algorithms need to be redesigned to actually fit the computation patterns over here. And we also need to rethink the theory of computing, because if you look at the theory of computing, it's very processor-centric today. It really doesn't fit this sort of model and this sort of environment where data access is really the bottleneck. It's bottleneck in terms of performance and energy. Okay, I'm going to skip these. But if you're interested in processing in memory, we have real processing in memory tutorials. One of them is coming up at ISCA. We cover a lot of interesting systems over here. I should say that we need to think differently from the past approaches. I think that's where storage-centric computing comes in. If you look at a storage device, this is an older version from one of our papers where we analyze a lot of reliability issues, for example, in modern SSDs. This is a system by itself. You can actually do a lot of computation over here. I think of this as a heterogeneous computing device with hybrid memory. You can actually make it an accelerator-based system as well. And it can enable data-centric design of systems and workloads. Why do we really offload things? Why do we actually treat this as just a storage device? This is really a computing device if you look at it internally. And I believe you can have application-driven customization that can make this a powerful data-centric engine. Maybe the processor should be actually serving the storage system as opposed to the other way around. So it's good to think about that. And maybe this is kind of what we're interested in doing in the longer term. Maybe these storage devices are connected to each other, and processors are also attached to them somehow as peripherals, let's say. And you have these applications that are driving the design of this storage system. The storage system is customized to execute them relatively fast. I'm giving you machine learning, genomics, graph analytics, and video. There are other important applications. And we find some primitives to actually accelerate these applications on this more storage-centric system. Okay, I will, and also I think having unified interfaces for efficient and fast communication is important over here. Now let me give you quick examples. I think there are two ways of looking into how to design data-centric systems. One is more traditional. That's what I call processing near storage. And the other is more disruptive. I'll talk about this less, if you will. I'll talk about traditional. I think if you look at processor and storage, or computing unit and memory units, today they're separate, right? The second one says, take the computing unit closer and closer, such that you actually integrate it in the storage chip in the, let's say, most tightly integrated case. The second one is fundamentally different. You have the computing unit and then storage. Forget about the computing. The storage itself is able to do analog computation. So any kind of memory device is actually capable of analog computation, and we can actually take advantage of that. I believe this is a lot more disruptive, longer term. There are reliability issues, etc. I believe these need to be combined in the long run, but this is easier. The second is easier to achieve. Now, let me give you one example from the second option, which is really computing near the storage devices. I'll give you an example from genome sequence analysis. There are many, many things to do over here, but one thing you do is read mapping. It's the first step in many genome sequence analysis today. Technologies are changing. There are other things you can do today without read mapping, actually, which is really interesting too, and we're working on them. But in read mapping, you align these reads from a genome to matching location in some reference genome. And this is an approximate string matching problem. And you find different degrees of similarity in the end. And this is actually, if you do it on a lot of reference genomes and a lot of read sets, this actually becomes hugely data-intensive problem. One reference genome, one read set, okay, that's not that interesting. But what becomes interesting is a lot of them at the same time. And this requires approximate string matching, as I said, and there are different errors and variation you need to tolerate. So how do we do it today? Basically, we move everything to the CPU, or accelerator, if you will, if you're lucky to have it. This has computation overhead and data movement overhead, huge data movement overhead, actually. Now, we have designed a lot of mechanisms, heuristics, accelerators, filters on this side to reduce the computation overhead and the data movement overhead on that side as much as possible, but the data movement overhead from storage remains. So the idea here is very simple, if you will. Why don't we do some simple filtering, simple offloading of functions to the storage system such that we don't have to move data, and we actually have a much more balanced system. You move very little data to the computation unit if you actually do that. And how do you do that becomes basically more technical. There are two, you need to basically fit the application, and the applications usually have exactly matching reads. This is easy to detect over here. And exactly, very, very divergent reads from the reference genome is also easy to detect. So these two things you can relatively easily do on the storage system. The question is, what else can you do? Can you actually move everything to the storage system? I think there's a lot to do over here. So again, there are details over here. We basically designed the SSD controller such that it has these specialized accelerators, which are relatively not so costly. But there are challenges also. You need to ensure that the applications are customized and you cater to the application behavior. And you need to ensure that you don't essentially, you take advantage of the limited hardware resources. I think this mindset needs to change also going into the future. Maybe we should not have that many limited hardware resources in storage units. Why do we have limited hardware resources in our storage and memory units? Because we're very processor-centric. Hardware resources can only be in the processor. If we break that mindset, we will have hardware resources in other places as well. And these other systems will have a lot more value than just serving the processor. Okay, again, I won't bore you with the details, but basically, you really need to customize the system for the application and the technologies that are generating these reads, if you will. And we did that. Let me give you some results. So basically, if you do this, what happens is you get rid of the computation overhead. Well, you reduce the computation overhead as much as possible using accelerators, and the data movement overhead also reduces. So you have a much more balanced system overall, if you will. And we see significant performance and energy improvements depending on the data sets you see. You can see that in some cases the performance improvements are more than 30x, and energy reductions are also close to 30x. And these are some, we compare to state-of-the-art software as well as hardware mappers, and you see that significant benefits across all of those. So exactly matching, it depends. Basically, the results depend on the data set, but overall, you get significant improvements. The question becomes, of course, how do you make these more independent of the data set? And that's something that we're tackling right now. We do a lot of area and power consumption analysis, and these things are not that costly to add, although there could be improvements going into the future as well. So this was just one example. I believe there are more examples, which I don't have time to go into in genomics. A lot of these accelerators that we've designed can be applicable on the storage side. Now, let me quickly give you the flavor of processing using storage, which is fundamentally different. I think this is actually longer term, but it's also quite interesting. Basically, if you look at the storage device or any memory device, it's able to do bulk bitwise operations reliably. And we have real chip results using this. Okay, I'm going to skip this one because it's a summary. But if you look at the data movement bottleneck, I've been motivating this. You don't want to move data over here. And then if you do in-storage computation, now your next bottleneck becomes the interconnect between the chips and the in-storage compute units. And that's what we want to tackle over here. How do you ensure that that bottleneck is not exercised? Well, do the computation inside these chips in an analog manner. And if you do that, actually, you get significant performance energy improvements, as I will show you. What is the idea? The idea is, if you look at any memory chip, you have some operands. These are bulk operands. And if you want to do some computation on these operands, you can do multi-word line sensing, multi-word line activation. You can do this in DRAM, SRAM, non-volatile memory technologies, and you can do this in flash storage, as we show in this work. You can do simultaneous sensing in operands, and that gives you a bitwise AND operation. So that's the idea, basically, this multi-word line sensing. And this is true in real flash chips. So what is the reason? Well, you simultaneously activate multiple word lines, and there are some word lines that you don't target. The ones that you target, essentially, target cells, if they store 1, they operate as resistors. Otherwise, they operate as open switches. And because of the principles of essentially how the memory operates, you get a bitwise AND function in the end. This is the example with 2 word lines. You can generalize it to multiple word lines, and you can actually do it across 48 word lines in a real flash chip. That's fascinating, I think. You get the bitwise AND. Now, how do you get the bitwise OR? This happens across different blocks. Again, I don't want to go into the details because we don't have a lot of time. But if you actually do the same thing across different flash blocks, not in the same flash block, you get a bitwise OR function because of the way these flash blocks are connected and they drive the sensing structures. And you do all of this with a single sensing operation. That's the interesting thing. OK, so that's bitwise and bitwise OR. Very interesting. Bulk bitwise. It could be across 16 kilobytes of data, and you could do it across many, many arrays, if you will. That's not functionally complete, but we already have NOT and NOT functions actually in the peripheral logic in flash memory. So you can have AND or NOT. As a result, you can actually remap your algorithms to this analog computing device, which already have digital to analog converters inside. And if you're interested, there's a lot more over here. But of course, the key issue to enable these things is, one of the key issues is reliability. How do you do this reliably? We did a lot of testing of real flash chips. And we have some mechanisms to actually improve the reliability. You need to use single bit per cell, unfortunately, in the current version. And you need to have precise programming of cells so that you can actually, you actually increase the programming latency a little bit so that you can actually do this reliably. And again, we have real system results, which you can read in the paper. We see that you can do this with a very small increase in sensing latency, less than 10% in the end. And we don't get any errors in the computation results in the applications we examine. So these are the applications. Some of the bitmap indices are great examples for this, for example, that's used in databases. And we see significant performance and energy efficiency improvements once you map the application to a system like this. Of course, this part is done in simulation because you cannot do an end-to-end system today. We're actually working on an end-to-end system where you can enable this sort of computation end-to-end in flash memory. OK, so that brings me to the end of processing using storage. I believe these need to be combined in the longer term so that you can take advantage of the best of both worlds. Because processing near storage reduces data movement a little bit. Processing using storage actually reduces data movement to its limits, in my opinion. And hopefully, both of them will enable fundamentally energy-efficient or data-centric computing systems. And also, these will be fundamentally high performance at the same time. I also believe that these could be fundamentally secure, but that's something to look into in the future. OK, let me conclude. So I think we're designing systems that are completely imbalanced today. We need to fix that. I teach the 600-student digital design and computer architecture class. And one of the principles that I teach to the students is balanced system design. And then I'm ashamed to actually talk about a processor-centric design that completely destroys that balance. So immediately, we're destroying the basic principle of design of our systems. I believe in storage, we can actually have an opportunity to make the systems a lot more balanced. And maybe the processor will be the peripheral, not the storage. OK, so I believe we need to think about data-centric, data-driven data-aware systems going into the future. We need to enable computation capability inside and close to storage. This can lead to orders of magnitude improvements. I've given you some examples. These are just scratching the surface, in my opinion. We can enable new application and computing platforms. I strongly believe this, actually, especially in genomics and machine learning, et cetera. And it can also enable better understanding of nature, but that's a subject we can leave for future. And who knows what else. So I think the future is bright. But of course, there needs to be a lot of research, design across the computing stack and adoption issues. So I think this picture kind of summarizes the nature part, if you will. If you look at this device, this is not a processor-centric device. And I will leave it at that. But that device also does a lot of optimization across the stack, as far as we know so far. So I will acknowledge my research group. You can take a look at some of the faces who have done some of this research. And we put a lot of work online. You can find our work online. And I'll thank you. And I'm happy to take any questions.
Questions, you can raise your hand, then we'll bring the microphone. No questions? Yeah.
Thank you for your good talk. You showed here like how you did the work around Genome, and there is work that was done for AI and others. So it seems like even though we're distributing the compute, now we are having like dedicated application specific compute nodes or computation resources, and eventually we'll have a lot of accelerators, which then we will explode again on the edges. How do you see the future in that direction, and how to make it a more general purpose computation entity that will be allowed to be programmable for each one of the applications?
Yeah, that's a great question. I think there are two types of answers I have for this. First is, we're having accelerators on the compute side. I'd rather have them on the storage side because they actually are fundamentally less data bottleneck. So that trend is already happening in the compute side. Why not also on the storage side? But the other more, let's say, researchy answer is, we should really be finding common ground across these applications and finding common primitives to accelerate in these accelerators. That's not happening as much on the compute side either, but I believe that should be happening on both sides, compute as well as storage accelerators side. Now, in some, I think it's going to be inevitable that in some cases, you will not find all the primitives you need. Some parts will need to be really application specific. I believe you can handle those parts using reconfigurable logic, for example, while giving up some of the downsides, upsides of ASICs. And also, I think there's benefits for having some general purpose CPUs as well. So I think when I say storage-centric computing, there are many things that go into it, of course. But I think one of the big potential directions is really pushing acceleration mechanisms inside the storage so that these data-intensive applications can become much faster and much more efficient. I believe that's relatively easy to do than completely basically moving everything to storage and the vision I mentioned where processor becomes peripheral. I believe we start step by step, look at which applications can benefit, and customize the storage system to the functions of those applications. And step by step, include more and more in the storage side, such that you see the benefits in those functions. I believe eventually you'll move a lot to the storage system so that you really get very high improvements. But I believe that's a relatively easy direction to do. And as I mentioned, I think the second part, if you can exploit the analog computation capability of the storage and memory devices that you have on the storage side, you can go to the next level. But I believe that's longer term.
So there was one more question over there.
Okay, sure. Oh, in the end, in the back.
Yeah.
Okay, thank you. I have two questions. One question is, in your speech, you mentioned we can use a filter near or in the storage, but I think the information how we filter the information relates to the application's operation.
Yeah.
So I want to know what information can we use, can we filter near or in the storage, maybe it's efficiency.
Yeah.
That's my one question. And the second question is, I think in the future, there are many or huge unstructured data. Can we use the similar method in such as AI or big data scenario?
Yeah. So to answer your first question very quickly is, you need to know the information from the application. So the application needs to provide information about what can be filtered on the storage side and what is the criteria for filtering. Exactly matching is one example. I'm happy to talk about it further. And the non-matching part is another example. So you really need to design the read mapper together with the storage system. But we try to minimize the changes to the application. So the application designer needs to write a function that can be offloaded to the storage device. So hopefully that's somewhat clear. If you want to know more, we actually have the code available on the GitHub, not in one of these places, but I'm happy to talk about it. The second part, generalizing it to unstructured data, I think that's a great idea. Yes, that's actually something that we're quite interested in. You have a lot of unstructured data, and genomics can be somewhat unstructured also, depending on what's generated. Generalizing these operations on different types of unstructured data with some common interface is a great direction.
Time, I think we need to stop the questions here and